And let's walk through the probability question from yesterday. I didn't do very well, but I think it was mainly because the first part I was not very familiar with the beta distribution because I didn't memorize it. We never had a question on this. And then part C, I misread the question. I think that was what happened. Part A, we have let P and Q be positive integers and let X be a random variable having beta distribution with parameters P and Q, meaning its density is this function over here. So from 0 to 1, we have this expression, and otherwise it's 0, so it's only in the 0, 1 region that we really care about. In the first part, we're trying to find the expectation of X. Okay, so if we're given a, what is it called? PDF function, then that means the density function. Then like what is it? If we sum from negative infinity to infinity, or in this case 0 to 1, then the area under the curve should always be 1. So over here, what we can do is we can just take the integral from 0 to 1 of this long expression, and it should equal to 1. So then we can rearrange it so that we move all the constants out to the one side, and then we have this expression of the integral is equal to this thing over here. And we can use this trick to kind of simplify the things. Okay, so yeah, in part one, what I did was I realized this, so I just moved it to here. Then what I can do is I know the expected value is the integral from 0 to 1 of x times its density function. So then what I can do is its density function I just found that is this thing over here from this. I just substituted that back in, and I have dx integral of this. Then what I can do is I extract the count constants out, and then I see that, okay, yeah, I'm matching the form of the above, this expression above. Except my A and B's are, um, my A is P plus 1, and my B is Q. So then I can write it in terms of this form over here. So then I would just have, let me erase this. I don't like to use blue most of the time. Keep it to yellow. So I have this form over here, and this is my constant. So I just simplify it, so that's P divided by P plus Q. I think this one is pretty straightforward. The minute you realize that the density function should sum to 1, and then you use that trick, you kind of avoid having to evaluate the integral, which the hint suggested. Okay, moving on. Second part. Supposing q is greater than 1, find the expected value of 1 divided by 1 minus x. Okay, so for this question, what we have to do is, since we're not sure what 1 over 1 minus x is, we can just treat it as a function that we plug in to expected value. So we have this inside here. This is equivalent to having a 1 over 1 minus x times our density function. From there, what we can do is we plug back our density function over here. Since q is greater than 1, we can be certain that 1 minus x here we could be able to cancel out from over here. So what we would get is still our constant x to the p minus 1 power, and then now here's q minus 1 minus 1. So then inside here, our a would be p, and our b would be q minus 1. And then this would lead to just some simplification of this would just be this. And then we would get p plus q minus 1 divided by q minus 1. Okay, I'd say the question is relatively straightforward, I say. But um let me reply to a message first. Okay, I'd say relatively. The first one is just not being scared by the beta and just kind of figuring out what you know. It's definitely doable if you don't know the beta distribution from this question. Mm, and then the second one, like the part two, uses the law of the unconscious statistician because I basically treated the 1 over 1 minus x as kind of like a function on its own. Kind of like this. I'll put this in. It's like what I did was I just treated the 1 over 1 minus x as another function, and I applied the laws, the unconscious statistician. I'll move it to here. So here what we have is we just treated th that function as g of x. And now we have our density function, which is just g of x times f of x, because we're just composed, right? And then usually what we do is x times the density function. But because we're asked to find g of x, we kind of just put in g of x, which would just be 1 over 1 minus x. So instead of having x times 1 over 1 minus x, 1 over 1 minus x replaces the x. So it's pretty powerful. Okay, let's move on to part B. Let u and v be independent random variables, uniform on from 0 to 1. Write the joint distribution density for u and v. Okay, so joint density for uv. I mean, both u and v are definitely independent. So f of u is equal to 1 because it's kind of just from 0 to 1 uniform, pretty straightforward. Um, it's a uniform, right? So yeah. F of u is just 1. F of v is also just 1. So f of uv, since they're independent, we can write f of u times f of v. And since each of them are 1, 1 times 1 is just 1 for uv in from 0 to 1. Part I is definitely pretty straightforward. It's just using dependence and you knowing that the uniform distribution is kind of just 1 because Um, it's 1 over b minus a. And our b is 1, a is 0. So 1 over 1 is just 1. Next part, compute E of u times max of uv. Okay, so how we're going to calculate the expected value is that E of u times max uv is equal to this. So we can break that down into two regions, where u is greater than v or u is smaller than v. So we're going to have the sum of two integrals. In the case that u is greater than v, we have u times, and then since u is greater, we're going to times u again, and then it's du dv. And then if u is smaller than v, then v is a greater one. So the max would be v, so it's u times v. And then over here, we're going to evaluate. We can't just write u greater than v, right? We're going to have to actually write the bounds. So we're going to first find the inner integral. So we're going to go from, since v is a smaller one, we're going to have to go from 0 to u and not exceed u. So that's why we're going to go from 0 to u. And the next u can go from 0 to 1. So that's why we have 0 to 1 over here. And then to determine the bounds on the other side, we're going to do u first, just swap the idea. Basically, u goes from 0 to v, and then v goes from 0 to 1. I think it's pretty straightforward. And then we just evaluate both integrals and we get 1/4 plus 1/8 is equal to 3/8. Yeah. Um, part three, we're gonna ask for the density for max of uv. Okay, so we're trying to find density. How we're gonna find density is essentially we don't have that much information. So the only kind of strategy we can go about this is to look at the CDV, CDF, find the CDF, and then take the derivative of that to find the PDF. I'd say this approach is pretty common because you can't just determine the density. That's way too hard. So what you do is you kind of go with CDF, which is easier, and then go backwards to PDF. So we're going to define our variable z to be the maximum of u and v. So the CDF of f of z is when the probability um, z is smaller than or equal to z. And then in order for both things u and v to be smaller than or equal to z, because z is a maximum of u and v. So that means that both of them have to be independently smaller than the small z. So that's how we have f of z um, is equal to p of z smaller than z. So that means our u and v have to be both smaller than z. Since they're independently smaller, then we can break it down into multiplication instead. And then we know from, because u and v are uniform, then we can kind of work this out. Um, Pu smaller than z is equal to z. Because like, if we're spread out on a uniform distribution, the likelihood of something um, being smaller than that is just a range from 0 to z. And then we're from 0 to 1, so that's just basically z. Think it's pretty straightforward. So since u and v are both the same distribution, then it would just be z squared would be our kind of CDF. And then PDF would just be the derivative of our CDF. So then we just take the derivative of this and we get 2z for z from 0 to 1. Okay, I think the major thing is just getting the idea of how to find density. Density can't be directly found, so instead we go from CDF to PDF rather than finding PDF directly. Okay, moving on to part C. A circular necklace of length n greater than or equal to 3 consists of n minus 1 black beads and 1 white bead, connected by n links. Three distinct links chosen uniformly at random so that all combinations of three distinct links are equally likely to be chosen are cut. So the necklace falls into three sections. For the part 1, for a given bead B, whose distance from the white bead is k links, compute the probability that it lies in the same section as the white bead. Okay, so for this question, when I was doing it, I kind of misconstructed the question because it's a circle where if you want to split it into three sections, you have to make three cuts, right? So then you have the three separate sections. I kind of misinterpreted it as like I cut two slices so that I don't know how I'm gonna get three pieces out of that, but that time I just thought that okay, I cut two times, I would have three pieces. I kind of was thinking more of it as like a I don't know, a a separate piece of string rather than a connected circular ring. So that was where it went wrong. But the idea is the following. I have n links and then all of them are connected, so it's like a circular thing over here. And then what I need to do is I need to make three cuts to three pieces. And I want to make sure that what is the likelihood that I have one of the beads and it's k away and it's still in the same section. So okay, so if I have k away, then this is sort of my region, right? Over here. This would be the region that I'm interested in keeping. I don't care where I make my three cuts, but I just want to keep it together. So I have kind of two ways to go about this. I could either just focus on cutting three slices um, somewhere in this section, in the outer like major arc, n minus k. If I'm able to cut three slices over here, three cuts over here, all inside this n minus k, then I would preserve my k, right? My k is preserved. Otherwise, I would just cut within the K. If I cut the K links between this, three cuts all within the K, then it also works because I just have the same section over here with the N minus K, my blue thing over here would be my thing. So no matter what, it's just the three cuts have to be concentrated in one region, either the pink or the blue. The pink has K links and then the blue has N minus K links. So that's how I get N minus K choose 3 because I either pick that or I go with the pink, which is K choose 3. And then I have total of choice of N choose 3 ways. So that would just be my answer. In part 2, I have I'm given okay, let's go to the question. In part two, compute the expected number of black beads in the section containing the white bead for the special case where n equals 7. Okay, expected number of black beads in the section. So the idea behind that is since I'm trying to count the expected, I can kind of use the indicator function to see if it's 1, which means the bead is in the same section as the white, otherwise it would be a 0. And I know that my n is equal to 7, so that means that I have 6 blacks and 1 white. So the my expected number of total blacks will just be the sum of how many I have each one if there's like as a expected value of the indicator function, right? So then that would just be the sum of the probabilities that the bead is in the same section um as the white bead. So that I was or if I break it down into the bead distance to the actual white bead, then I can just use the part one I just did. Essentially, what I do is I have one, like basically imagine I have a white bead over here. And then what I do is, okay, I have, if I'm in a circular loop, this one is one away, one link away. If I'm one link away, I can just plug in the earlier thing, would just be the formula of this. And I would get 20 over 35 because I'm just plugging in one to that formula. And then the same goes for the next bead. The next black bead is 2 away. So then I would just plug in 2 to that distance and I would get the same. The next would be 3. And then the next would be 4. And then 5. And then 6, right? It would just be 1, 2, 3, 4, 5, 6. But then I can realize that for the 4, it would just be 3 away as well because it's a loop. So on the other side, it would be the same. And then the next one, the 5, would correspond to 2, and then the 6 would correspond to 1. So then I would just have to calculate just 1, 2, 3, and then just double that amount would just be my answer. So I get this. And my expected value would be 2. I think the major thing about part two is kind of thinking about the indicator function because it could either be one state or the other. And then once you know that state, you can kind of use part one so that you kind of don't have to list the conditions rather than like yeah, you can just calculate it based on the formula you have rather than have to count all the cases one by one. Because that was what I did. I just did it systematically. Okay, cool. That's it for this problem. I think the relative takeaway for this question that was kind of difficult was kind of knowing the beta distribution, but it ne doesn't necessarily have to use it. But the major trick is that the area is always like under a density function is always equal to 1. That's like the big takeaway over here. Then this takeaway is just using Lotus as the as thing to simplify, just basically making that a function. And then the joint density function, yeah, just this is just independence. Um, this is just independence. E of u of this, yeah, breaking it down. This one is definitely case two integrals, breaking it down into two cases, case one and case two. Density, yeah, density, you want to go from CDF to PDF. Differentiate. Part C, yeah, definitely just read the question and kind of just go with it. But the idea is that the next one, find the expected number, break it down into the indicator function. Cool. That's it for today.